In this video, we're going to take the final step and actually define the derivative, which is going to mean the velocity, for a parametric curve or a vector valued function. We're going to start at a generic point A on a curve. So imagine a trajectory defined by r of t. We're going to fix a point of time, t equals a, and that'll be our start point. And based on that, we're going to take a small increment of time beyond there. So we're going to take a small step in time of delta t, and that's going to put us at t equals a plus that little bit of change. We can then, of course, calculate the average velocity over that time interval. What we do is we take our formula for the average velocity, which is our displacement divided by the time interval. And our displacement is going to be our position at the end, which is a plus delta t, minus the position at the start, which is at time a. So those are going to be vector valued quantities. And divide that by the time interval, which is simply delta t, or if you like, we could have gotten there by a plus delta t minus a. The a's cancel, and we get delta t. Now if we take a careful look at the ingredients here, the displacement is a vector quantity. If we take any 2 points, we can connect them with a vector. The time interval, however, is a scalar quantity. So what we're doing is taking a vector and we're scaling it, applying a scalar transformation to it, or changing the length of it by dividing by delta t. Now to keep things general, what we often do, or you'll often see in textbooks, is that instead of delta t, we use delta h. So in this case here, we represent the average velocity as the change in position as a vector over the value h, or we would write it as a plus h, the position at the end, minus the position at the start, divided by h. Again, n minus start position. That doesn't change any of the nature of anything in our calculations. This is still a vector quantity. This part here is still a scalar. It just takes the idea of a small time interval and replaces it with a single letter. I'm personally not convinced it makes things any clearer, but it doesn't make things more generic. So we keep it in there as it's something that you might often see in other analyses or papers or textbooks. Having now defined the average velocity, we can take the final step to turn this into calculus and make it the instantaneous velocity. So if we want the velocity exactly at the time a, then what we're going to do is let our time interval go to 0. So the instantaneous velocity is going to equal exactly what we had before, a plus delta t. Keep the color scheme going. So at the endpoint minus the start point, position at the endpoint minus the start point, dividing all of that by the time interval, delta t, and the only change we make to convert this to an instantaneous velocity is we take the limit as delta t approaches 0. Notice that makes both the numerator, the displacement, smaller and smaller, but it also makes the time interval smaller and smaller. And the magic of calculus is that there is a perfectly valid velocity quantity that we get out of that when we're done. This is, of course, why we study limits as a separate topic, because this is effectively a 0 over 0 limit. So we have to handle that carefully. But fortunately, most of you will have seen how we handle those kinds of limits in your earlier courses. It turns out there's a nice way to handle them in almost every practical case for calculating velocities. We'll see a bit more of that in the upcoming videos.